guys, this is going to be the first video of our new unit, lesson 5.3, solving trigonometric equations. So we are going to be solving equations that have sine, cosine, tangent, all those things in it. I think for this first video, I'm probably only going to be able to work examples 1 and 2. Like I said, I think I said this before, I don't want to make these videos much longer than 15 minutes. So if I'm getting close to that point, I will probably stop, and then I'd like to also do example 3 for this first assignment. So I may make that into another video. Okay, this is on, if you want to follow along in your books, we are on page 362. And I want to look first actually at the introduction in the book. So hopefully we can, oh good, that's a good size. Alright, so we're here in the book on the very first part of lesson 5.3. Now, under the introduction, we're just going to look at this together, okay? So it says, to solve a trig equation, use standard algebraic techniques. So just like you'd solve any other equation, except your first goal in solving a trig equation is to isolate the trigonometric function on one side of the equation. Meaning, before you get x all by itself, you want to get sine x all by itself. Once you get to that point in these first parts, you should be able to solve it. So, for example, if this is your equation, 2 sine x equals 1, you would divide each side by 2 to get sine x all by itself. Now, when you get to this point, sine x equals 1/2, you know from your circle, here I'm going to pull up I'll show you a unit circle first. Sine is the y values, so you know that when sine x, that when the sine is 1/2, sine is y, then you're at pi over 6. You're also, if we can get over here to the other side, when y is 1/2, you're also at 5 pi over 6. So you have two answers here. But the thing about these sine functions is that they go on forever, right? We have two versions of them. We have this unit circle version and then the graphical version. So you can see here that we're at 1/2 at all these points. So there's multiple solutions. There's actually infinitely many solutions every time you make another rotation. So our answer is actually going to be pi over 6 plus 2n pi. I don't like the way that's written. I would write n times 2 pi. But we'll get to that here. We'll work an actual example. I just wanted to give you a little introduction here. And as we work the example, you'll see how we can get an infinite number of solutions. All right. Oh, I need this. Okay. So we're going to do example 1 together, and it'll become more clear. So let's solve sine x plus square root of 2 equals negative sine x. Just like solving any equation, you want to get like terms together. So I'm going to bring this sine x over here with this sine x. So I'm going to subtract from both sides. I'm left with the square root of 2 equals Negative 1 sine x minus 1 sine x gives me negative 2 sine x. Remember, my goal is to isolate sine x, so I'm going to divide by negative 2 on both sides. And I end up with negative square root of 2 over 2 equals sine x. Now this should look familiar by now after doing your unit circles. You should recognize this, the square root of 2 over 2 goes with all of the fourths on the unit circle. So we know you can, again, you can bust out your unit circle, but also know that if you don't have your unit circle with you, you can always create it, right? So if you need to just draw it real quick, we've got 0, then 1/4, 2/4, 3/4, 4/4, 5/4, 6, 7/4. Sine applies to the y value. So where on here is the y value negative? So we've got obviously positive y values up here and negative down here. So this is 1, 2, 3, 4, 5/4, or 5 pi over 4. This point is negative square root of 2 over 2 square root of 2 over 2, right? So here, oh, sorry, my bad. That one's also negative. So we have, here we have a negative square root of 2 over 2. Oh shoot, my screen just kind of died. Why did it do that? It's okay. We're still recording, so I'll just have to look through my phone. So we also have a negative y value here at 7 pi over 4. So we've got two answers for x. So x could equal 5 pi over 4, and x could also equal 7 pi over 4. But remember how we talked about the coterminal angles, how if you went around again, you could get back to this same angle? That's what the infinite solutions is all about. So we could keep going around this circle, just keep adding 2 pi, right? And getting back to this angle. So 5 pi over 4 plus 2 pi would be, that's what, 8 pi over 4, so 5 plus 8 is 13. So 13 pi over 4 would also have that same coordinate. Then you add 2 pi again, and again, and again. You keep getting this same answer. So we say 5 pi plus any number times 2 pi. So n just represents how many times you go around this circle. Right, so same here. So 7 pi over 4 plus however many rotations you go around this circle. And the reason we use 2 pi is because the domain for sine and cosine, or a period, I should say a period of sine and cosine is 2 pi. Okay, example 1. Done. Let's move on to example 2. Let's see something real quick. Wish I knew why my screen stopped. Okay. Solve 3 tangent squared x minus 1. Again, we want to isolate the tangent x. Remember, when you see tangent squared x, this is the same as this. If it's helpful to you to rewrite it like this, you can do that. That might help make a little more sense for you if this is confusing. But those are the same thing. So we start just by adding 1 to both sides. We get 3 tangent squared equals 1. Then we divide by 3. And we get tangent squared equals 1/3. Now our next step is to take the square root of both sides. When you take the square root, remember, you always get a positive and negative. So we have tangent x equals positive or negative. The square root of 1 is just 1 over the square root of 3. Now we can't have square roots in our denominator, so we're going to multiply by the square root of 3 over the square root of 3 to get rid of that. Remember, if I'm going too fast, you can always pause and get caught up, okay? Now we have positive or negative square root of 3 over 3. You just did that tangent assignment. This should look familiar. I'm hoping that by doing that tangent assignment you were able to see the patterns. So let me, I'm going to get off the chart real quick. So here's the chart. Hopefully you guys still have your chart. We have the square root of 3 over 3 showing up in positives or negatives every time we have a sixth. Do you see that? And here a sixth and a sixth. So that's where you're going to see your square root of 3 over 3 is always at the sixths. That's a weird word to say. I also have this circle. Oh, no, that's the wrong one. Probably have to zoom out for you to see it. So here, so the tangents at every, when it's simplified to a sixth, not like it's 4/6 and it simplifies to 2/3. When it's simplified the whole way and it's a sixth, that's where you're going to find the tangents being either positive or negative square root of 3 over 3. So at 1/6, 5/6, 7/6, and 11/6. I can't say that. Okay, so also the period for tangent, I'm going to zoom back in, see if I can get that zoomed into how it was. Is that good? Maybe a little more. The period for tangent is just pi, remember? And the reason for that, look at your chart here again. So, I'm going to see. Okay, so see tangent. Do you see the pattern here? So this is from 0 to pi. Here's your pattern. It's the exact same pattern from pi to 2 pi. It's exactly the same. So the period length is only pi. You could add pi to any one of these numbers and you'd get back to the same point. Whereas sine and cosine, it's not the same. It's changing. It's different here and here. So you have to go through the whole 2 pi to get all your options. All right. So all that to say, when tangent x is positive or negative square root 3 over 3, we would be at pi over 6, or what do we say, 5 pi over 6, right? Yes. You do not have to put anything after pi, anything down in the 3rd and 4th quadrant, because those will be covered with this when we say plus n times pi. So the tangent will be this at pi over 6, or any number of times pi. Sorry, plus any number of times pi. Does that make sense? I don't think I said that right, but you'll get the idea. Same here with 5 pi over 6. Let's see, and how long are we? Ooh, we're at 16 minutes. That was really long. Okay, I'm going to stop there, and I'll make another video for example 3.